In this presentation, we'll explore database partitioning, focusing on horizontal partitioning and sharding techniques. Learn how to scale databases effectively through intelligent data distribution. Database partitioning is the process of dividing a large database into smaller, more manageable pieces while still maintaining logical relationships. This approach provides several key benefits. First, it improves performance with faster query execution because of reduced data scanning. Second, it enhances scalability by efficiently handling growing data volumes. And third, it simplifies maintenance through easier backup, recovery, and administration. There are primarily two types of database partitioning. The first one is vertical partitioning, which involves splitting tables by columns. For instance, you might separate frequently accessed columns from rarely used ones. The second one is horizontal partitioning, also known as sharding, which involves splitting tables by rows. This is commonly used to distribute data across multiple servers. Horizontal partitioning, often referred to as sharding, involves distributing the rows of a table across multiple database instances. Consider a scenario where you have an original table with 1 million users. Sharding allows you to divide this table into multiple shards. For example, Shard 1 might contain users 1 to 333,000, Shard 2 contains users 334,000 to 666,000, and Shard 3 contains users 667,000 to 1 million. There are several techniques for implementing sharding. The first one is range-based sharding, which involves partitioning data based on value ranges. For example, users with names from A to M might be stored in Shard 1, while users with names from N to Z are stored in Shard 2. The second one is hash-based sharding, where a hash function is used to determine which shard a piece of data belongs to. For example, the hash of a user ID modulo 3 could determine the shard number. The third one is directory-based sharding, where a lookup service maps keys to shards. A central directory maintains the mapping of keys to their corresponding shards. The fourth one is key-based sharding, where partitioning is based on specific key attributes such as geographic regions or customer types. Let's look at an example of hash-based sharding using a Python implementation. The function get_shard takes a user ID and the number of shards as input. It then returns the hash of the user ID modulo the number of shards. For example, if the user ID is user_12345, and we have 3 shards, the function calculates the hash of the user ID, finds its remainder when divided by 3 and assigns the user to the corresponding shard. So the user ID user_12345 will go to shard 2. Sharding offers several benefits. It improves query performance, enables horizontal scalability, reduces hardware costs, and provides better fault isolation. However, it also presents challenges, including complex cross-shard queries, data redistribution overhead, maintaining data consistency, and increased operational complexity. When implementing sharding, there are key considerations to keep in mind. Shard key selection is crucial, so you need to choose keys that ensure even data distribution and minimize cross-shard queries. Load balancing is also important. Monitor and rebalance shards to prevent hotspots and ensure optimal performance. Plan for data growth and have processes for adding new shards dynamically. Implement appropriate consistency models and handle distributed transactions carefully. Successful sharding requires careful planning, monitoring, and the right architectural decisions. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.